particular video, we'll be writing a program of code, MATLAB code, for economic dispatch problem, including the generator limits and excluding the losses. Now, I have divided the entire program into 5 parts. So these are the 5 parts. The first part is the initialization as well as the data entry. So whatever it should be actually data entry and initialization. So whatever data is required, the data is retrieved, and the necessary initialization has been done in this particular step. The next step is to calculate the generation of each unit, neglecting the limits. So coming to part 1 and part 2 will be same as that we have done in the previous program, that is economic dispatch problem, neglecting limits and losses. So whatever code is there, the same code can be used to do part 1 and part 2. So it is similar to the previous program. Now the actual work starts from part 3. Now in this step 3, we will check how many units are violating its limit, whether it can be violating its maximum limit or it can be violating its minimum limit. So we will check for those units which have violated its limit, and we will, in the next step, that is in the step number 4, I'll divide the entire units into 2 parts. One is violating units, second one is non-violating units. So violating units are those which after step 2, the generation, if the generation of those units have beyond its limit, such units I call it as violating units. If they are within their limits, then such units I call it as non-violating units. Clear? So now here in this part we will be differentiating the units based on whether it has violated its limit or not. So that part, that differentiation or that classification of the units will be done in part 3. In part 4, we will take only violating units and we will fix their generation, or if I can be more technical, we will peg their generation value to its maximum or minimum value. Like if out of 3 units, unit number 3 has violated its limit such that its generation is more than its maximum value, then we will fix the generation of unit number 3 to its maximum value. Or if I say, if out of 3 units you have unit number 3 or unit number 2 which has violated its limit such that its generation is less than its minimum value, then I'll fix its value to its minimum value. So if I take an example here, I'll just put an example, that way it will be more clear. So here we have units, so unit 1, 2 and 3. So the maximum of this particular unit is 100 and this is 500. This is P max value and this is P minimum value. Clear? So and for unit 2 it is 50 and 200, and for unit 3 it is 200 and 700. Clear? So this is how the data is given. There are 3 units, each this should be the minimum value and this has to be the maximum value. Okay, so this is the minimum limit of all the 3 units and this is the maximum limit of the units. Now, so after step number 2, okay, so yeah, after step number 2, so the generation was found to be so here it was around 150 and this was around 230 and this was around 150. Sorry, not 150, I'll take it as 350. Okay, so this was the generation we got. Now, so this is the it is just a sample data, it is not an exact data. I have just taken this data as an example. Okay, now after the economic dispatch calculation, this is the result we have found. So now we will check those units which have violated its limit. So coming to unit number 1, so it is, the generation is 150. This is within its limit, so this is within its limit, so I'll make it, okay. Yeah. Now coming to this particular unit number 2, so the generation is 230. You can see that the maximum value is only 200. The unit number 2 is actually violating its limit. So this is a violating unit. Coming to unit 3, again this is within the 350, this is within the limit, so this particular is within its limit, so this becomes your non-violating units. So out of 3 units, unit 2 becomes your violating unit and unit 1 is your non-violating units. So along with unit 1, we also have unit 3, which is non-violating unit. Okay, so this is this particular part, differentiation of difference unit, this will be done in step number 3. Now in step number 4, we'll fix the generation of violating units to its minimum or maximum value. So that is done here. So I'll just tell. So now we'll fix. So only unit 2 is violating its limit. So I'll fix the generation of this unit to its maximum value. Now if in case, if the generation of this unit was around 40, so if it was around 40, then we would have fixed this generation to its minimum value, because this value is below its minimum value. But what we have got is 230. This particular value is above its maximum value, so then we will fix this generation to 200 megawatts. So these values we will not calculate now. So we will not be calculating anything for unit 1 and 3. So for unit 2, we have fixed its generation. Okay, no calculation will be done for unit 2. Now once we have fixed this value, the next part is to adjust the generation of non-violating units. Now this value is fixed for unit 2. What should be its generation, that has been fixed. Now we need to calculate the generation for unit 1 and unit 3, that is non-violating units. Now for these units, that is units 1 and units 3, we will follow the similar calculation that we did in step number 2. So using the similar calculation, we will calculate the generation. So during this calculation, we have to make sure that we have excluded the non-violating units. So coming to this particular example, we will exclude this particular unit, that is unit 2, and we will do the calculation. Like if you have 3 units, for in step number 5, again economic dispatch neglecting limits calculation will be done only for 2 units, that is unit 1 and unit 3, and we'll calculate the generation of those 2 units. And at the end, we have to make sure that the sum of all these 3 should be equal to the power demand. Okay, there is one more thing that we need to keep in mind, that is the Kuhn-Tucker conditions. So this is given by the Kuhn-Tucker conditions. For those units which are within its limit, like after unit 2, after step 2, for violating non-violating units, I'll repeat, for non-violating units, the incremental fuel cost should be equal to the new lambda. Now in step number 5, we'll be calculating the new lambda value. So the incremental fuel cost of those units, like for example, the incremental cost of unit 1 and unit 3 should be equal to the new lambda that is being calculated in step 5. Okay, that is the first condition. The second condition, if you have fixed the generation to its maximum value, then the incremental fuel cost of that particular unit should be less than the new lambda. If you have fixed the generation to its minimum value, then the incremental cost of that particular unit should be greater than the new lambda. So like now in this is violating its limit, and you have fixed its value to its maximum value. So if in case from unit 1 and unit 3, the new lambda value is around 15 rupees per hour, then the incremental fuel cost of this particular unit 2 should be less than that value. So this particular Kuhn-Tucker conditions will be more explainable when we when we run the program and get the result. So there this particular Kuhn-Tucker conditions will be more explainable. Okay, so now I'll go to the program part. So this is just now whatever I have explained here, this is the structure of the entire program. So here is the actual program. So coming to part 1 and part 2, I have told you it is same as the earlier program that we've done. So in this case I have directly taken the data to like I was just trying with the program, so every time I don't want to enter the data, so that is the reason why I have taken the data directly. Okay, so next is initialization. So all the initialization will be done as per the previous program, and we will calculate the P, that is generation. Now this is till here, this is part 1, that is initialization and data entry, and this particular thing is part 2, that is step number 2. Now we will check if any generator is violating its limit. So for that I have taken two variable, v equal to 0, sorry this is not there. Okay, v equal to 0 and s of ng is equal to 0. Now this is a scalar quantity and this is a vector quantity. Now this particular v will tell if the generators have violated its limit or not, but it will not tell you which units have violated its limit. Like it will only tell yes there is a limit violation. It cannot indicate, or it cannot identify which unit has violated its limit. Now in order to identify which unit has violated its limit, I have another variable initialized, that is s of ng is equal to 0, which means that s is a vector of 3 elements. 3 elements or number of, it's based on number of units. So those things I have initially initialized it to 0. Now for example, after this calculation, if s of 2 is equal to 1, which means that the unit number 2 has violated its limit. If s of 2 is equal to 0, it means unit 2 has not violated its limit. So that is how I'll be checking if any unit has violated its limit or not. Okay, now next is to code to generation. This is part 3, that is a code to fix the generation of violating units to its maximum or minimum limit. So I'll be having a for loop from I equal to 1 to ng. Now the first thing is we will check if any units have violated its limit. So I'll not be going for like minimum limit or maximum limit. So first thing is for a general, if any generation is within its limit. If it is not within its limit, then this particular code will be executed. It will be equal to 1, and then the next the code will enter into this particular region. Now here we'll be more particular whether the unit has is below its minimum value or above its maximum value. So I can even exclude this part. This is not needed. So I was trying with the code. That is the reason why there are few things which are not needed actually. Yeah, so if the limit is below its minimum value, then the generation will be fixed to its minimum value. If the generation is above its maximum value, then its generation will be fixed to its maximum value. So this is a simple way of fixing the generation of violating units. Now we need to adjust the generation of non-violating units according to the generation of violating units. Now this particular program is similar to program used in part 2 with slight modification. So all the initialization is same as that. Now here the program will enter into this particular loop only if v is equal to 1. This means that only if there is a limit violation, only then the program will enter into this code. So that is the reason why I have added one more condition for the program to enter into this while loop. Clear? So next again the same program. Yeah. Now here, uh, the same code I have used, the similar code that was used here, the same code I have used for the part 4, that is fixing, but only with some extra condition. Now here you have two conditions, like, sorry, yeah, this part. Okay, so the same program is used only with one extra condition. If Si is equal to 0, which means that if any unit is not violating its limit, only then this particular calculation will be done. This entire calculation will be done. For those units which have violated its limit, we have already fixed its generation, so no need to fix its generation in this particular part. So this if statement will make sure that the generation is calculated only for those units which have violated its limit, sorry, which have not violated its limit. I'll repeat, the in this particular code, like in this part 4, the generation will be calculated only to those units which have not violated its limit. So that particular condition is checked by this if statement. Okay, so then similar calculation will be done, and we'll calculate the lambda value, and at the end we will calculate the incremental fuel cost of all the three units. So this is how the entire program is written. Now I'll just run this program in MATLAB. Okay, so this is my code. Now whatever code I had copied, the same code is here. Now this particular part, it is for general program. Okay, this is I've put a comment section. This is within the comment section, so this part will not be executed. So this is ABC value, minimum and maximum value of all the generating units. Now initially I'll fix the generation to around 550. Sorry. So this is the initial demand. 550 is the initial demand. Okay, and the same code, I'll run this code. So okay, yeah, now you can see that the generation is this much, and this is the lambda value, and here you can see the incremental fuel cost of all the three units is same as that the lambda value. Now you can see here I'll show you the limits, or I'll run the program again such that these values have been clearly visible. That way you can get a clear picture of the program. So I'll run it again. Okay, so now you can see that this is the generation. You can see this is for first unit, this is within its limit. For second unit also this is within its limit, and for third unit 300, 650, so generation is within its unit. So no units have violated its limit, so the lambda value will be 9.6542. So this is the incremental fuel cost of each unit. So in this case this will be equal to the lambda value. That is the major condition of economic dispatch problem. The incremental fuel cost should be equal to the lambda value. The next, I'll make a small change in the program. I'll change the power demand to 1500. So now I'll execute the program. So now you can see that initially this was the result we got after without including the limits. So this was the limit. So here you can see the first unit is within its limit, so it is a non-violating unit. Coming to the second unit, the generation is 431, but the limit, the maximum limit is 300. So unit 2 is violating its limit. Similarly, unit 3 is also violating its limit. So now we are fixing its value to its minimum or maximum value. Since both the unit 2 and unit 3 is above its maximum limit, we'll be fixing their values to its maximum limit value. So this is the result you get after fixing the particular generation. Okay, now this particular value is something that needs to be calculated. Okay, now directly based on the demand, we have 1500 as the demand. These two values have been calculated, so we can fix this value to 1500 minus 300 minus Yeah, this is after fixing. This is the program after fixing. So minus 1500, minus 300, minus 650. So then this is the value. We can calculate the demand, but sometimes what happens if there are more number of generation, so you will not be having one non-violating units. You may have more than one non-violating units. So then you need to go for economic dispatch problem again. Okay, so after the calculation here, you can see that this is the final generation. So this is fixed to its minimum and maximum limit, and this is the generation of the non-violating units. So the lambda value was found to be 15. Now based on Kuhn-Tucker condition, the incremental fuel cost of those units which are within its limit should be equal to 15. So here you can see this is equal to 50. And the last second condition is, if you have fixed its generation to its maximum value, then the incremental fuel cost should be less than the new lambda value. So you can see here the new lambda value is 15. The old lambda value is not given here. I'll just check here. Okay, we can just it's not needed actually. Okay, the new lambda value is 15. So here you can see for unit 2 and unit 3, its incremental fuel cost is less than 50. So here, so then you can say that this particular program is satisfying the Kuhn-Tucker conditions. Thank you.